The aim of this project was to create a signal generator that could be used to test ECG signal conditioning systems. In the top right corner we can see the structure of an ECG signal. Each part of the signal will be generated separately and then they will be added up. Signal components R and S are generated by the first 555 timer. It outputs a square wave, which passes through a modified differentiator. The frequency of the signal produced by this 555 timer also becomes the frequency of all the other component signals. The Q component is generated by this circuit. It consists of two simple delay circuits made with capacitors and comparators, controlled by the output of the first 555 through MOSFETs. This solution was used because different component signals need to differ only in phase shift and amplitude. The frequency needs to be identical for all of them. The phase shift is obtained by changing the capacitance and resistance of the elements used in the delaying circuits. The exact mechanism will be explained in the second part of the video. The circuit generating the T component is very similar and works based on the same principles. The P component was the hardest to produce due to high phase shift relative to the signal generated by the first 555 timer. It turned out that 3 delaying circuits and another 555 timer were needed to obtain a signal with appropriate phase shift. For the final output nodes, voltage dividers are used to create signals with realistic amplitude of several millivolts. In addition, inverter gates are used to switch between mostly low and mostly high square waves as needed. In the end, the components are added together by the summing amplifier to obtain the final ECG signal. Let's investigate how the delaying circuit works, as it is the source of all the component phase shifts. This is the signal sent from the first 555 to the MOSFET. Each high pulse makes the MOSFET connect the capacitor to VCC, rapidly charging it. When the 555 signal goes low, the connection through the MOSFET is severed and the capacitor begins to slowly discharge through the resistor until the next high pulse is received. The plus pin of the comparator is connected to the capacitor, and the minus pin to a voltage divider that creates constant voltage. The comparator changes its output when these voltage functions intersect. Here we can see how the comparator's output depends on both voltages. The first charging curve of the capacitor determines the phase shift of the signal. I'm also working on a PCB version of the project. The circuit needs exactly 6 inverter gates, so I'm using a hex inverter IC called 7404 to deal with all the signal inverting. I added pins for connections with the power supply and with the signal conditioning circuit. This is how the project looks like in the 3D view.